Hello, it's Mr. Fiedler. I'm going to now review the difference between an ideal gas and a real gas. Now, an ideal gas is what it sounds like, right? It's ideal, it's theoretical. And we said with the kinetic molecular theory of gases that there's a few assumptions we make there. One is that the volume. These people looking at me funny again. What?
You guys all right?
Yeah,
Wow.
just making some videos.
Yeah.
Yeah,
When did it happen?
yesterday.
Sorry.
Yeah.
Here, did it hit the house at all?
Oh, yeah.
Okay.
Eh.
Everyone safe though?
Yeah.
Okay.
Yeah, thanks.
Wow.
It must be the shave, right? I don't know why they looking at me so funny. The lady stopped, like asking me if everybody's all right. Strange. Hello, it's Mr. Fiedler, and today I'm going to talk about real gases, ideal gases versus real gas. Now, ideal gases is what it sounds like. It's ideal. It's theoretical. And so let's review first on ideal gas. With the ideal gas, the molecules themselves don't take up any space. Now, that's how we assume they behave, and we have an equation, we can calculate some things with that. But in reality, they do take up space, right? A molecule, even though it's very, very small, it does take up some space. The other thing about an ideal gas is we make some assumptions that there's no attraction or repulsion between the particles, that they behave like billiard balls, right? The one billiard ball can hit the next, bounce off, no energy's lost, nothing happens. In reality, we know that's not true. So let's look at how a real gas behaves and then what happens to the pressure and the volume, how that differs from ideal gas. Now, here's a little drawing of the volume effect, right? Okay, the volume effect. So if we look here, I have a drawing of an ideal gas. And what I'm showing here is the molecules. And essentially we're saying, here's these molecules of gas, these particles of gas, and we don't even count their volume. The volume is all empty space, and forget about what their volume is. But if I drew it like this here, that shows all the gas particles all, like, say, touching each other, I mean, this wouldn't happen, but you can see that a real gas does take up some volume, right? So we have to consider that that size of all the individual molecules do take up volume in a real gas. The larger, the heavier, the larger gas molecules, the more volume they take up. Now, what about pressure? Okay, the pressure effect. Okay, now, with an ideal gas, the particles move around, they hit the wall of the container, they push outwards, their energy helps to push outwards against the wall of the container, and that's what makes pressure. And so what we're saying with an ideal gas is there's no intermolecular forces, which we know is totally untrue, right? There's intermolecular forces that can attract and hold one molecule to the next, even if it's nonpolar, right? Those are the London dispersion forces. So, drawing an ideal gas, we say, okay, there's no repulsion, there's no attraction, these particles just fly around, and they make pressure by striking the insides of the container, okay? But with the real gas, we know there are IMFs. There's intermolecular forces. Okay, so in a real gas, we do have intermolecular forces, even for nonpolar molecules. Okay, so the charges, the plus and minus, the attraction and repulsion of the intermolecular force can essentially slow down the particles. I sometimes think of it as like it makes them a little bit sticky. Okay, they might collide with one another. They don't stay bonded together, but it slows them down. They lose some of the energy in the collision because of the intermolecular force. So I kind of drew it like this to see what happens to the pressure. The actual pressure at a real gas is lower than we would expect, right? Lower than calculated with the ideal gas law. Why is that? Here's I drew like a gas molecule with a plus minus charge. And it's flying along, and the minus side of it here clips the plus side of this gas molecule. It's a little bit sticky, a little bit slows it down so it has less energy when it collides with the wall of the container. And so if it has less energy when it collides with the wall of the container, the actual measured pressure will be lower with the real gas than what we'd expect to see if it was ideal gas. Okay, so next I'm going to show you the modified equation called the van der Waals equation. And that's an equation where we can make adjustments for pressure and volume because gases truly are real.